Okay, so let's get started with this piecewise function. So this is week 7, lesson 4, as you can see on the left. In piecewise functions, I'm just going to run through this this entire slide and talk about it. If there's any points that you want re-explained or just elaborated upon a bit further, let me know through an email. But otherwise, I'm just going to go through these slides and talk about what these might mean. So piecewise functions, it's the last type of graphs that we'll be dealing with. It really just means if we have a graph, it really just means we are using more than one equation. So maybe from 0 to, I don't know, like here, we'll use one type of graph, but then we stop, right? We don't just carry on with this quadratic or whatever it was. But we say it only applies up to here, and then maybe we have a straight line graph from here on out. So we have two separate equations for this section. We'll have some equation y equals something, and then for this section onwards, maybe we have another equation, and it just and we have two separate equations patched up together, and we say, oh yeah, from this point to that point. So when x is 0 or up to whatever this point is, it's this equation that we work with if you want to know any of these points here. But if the x is larger than that by any chance, then we're dealing with whatever this equation is. Yeah, so and then if you want to find out, you use this equation to work that out. And this equation doesn't apply anymore for this area where x is larger than this point here. So we are just saying we're using more than one equation, and we are, and it's just going to be dependent on what area, what value of x we're talking about. So here's an equation. Now it's written in a written in a certain way. Fx just means the function, or it just means the equation or the value. We sometimes use y for this, so it's almost the same thing as y. It just means this fx just means some function that's dependent on x, right? Which is what normally is, right? Because we write y in terms of x, right? Some there's maybe x squared in there, maybe there's a 2 to the power of x in there somewhere, or whatever it is. We know y is in terms of x. So this f business here, the function, you can understand it to be similar to the y that we've been using. Cool. Now, okay. Now, in this example, we have something that's drawn like that, and we have it's 2x for this, and it's something else, x minus 1 for this. So this is in the slide. So what this means is when x is less than 3, right? So let's say we have a graph, and let's say this is 3 here. When x is less than 3, all of this area here, anytime we want to work with that area there, we know we're going to deal with this equation, 2x, which goes something like that. Yeah, I know it's not an accurate drawing, but just to say. But from here on out, so when x is 3 or more, so at x is 3, we use this value now. We don't use this value anymore. So if I said, oh, how high does this graph go at the point where x is 3? We don't use this one. We use x minus 1, because this one is x is greater than or equal to 3, as you can see in that right there. Cool. So from here on out, I wonder if it links up. So it's a less steep graph, isn't it? Something like that. I wonder if it links up. It might not link up at all. Yeah, like it might start from here, and then go up like this, but less steep. Oh no, it's drawn in the thing. Oh, what am I doing? It's drawn in the thing. So Yeah, and it just goes on, and this goes on backwards here. And we're saying, cool. If I ask you, oh, what is the value when x is 2, and you want to find this value here, we just use this one. We use that first equation, 2x. If I ask you, oh, what is it at 7? When x is 7, what's the thing? We don't use this equation anymore. We don't use 2x for that, because when x is greater or equal to 3, greater than or equal to 3, this equation applies now. So right, so we use x minus 1 to find out what the function, or what y would be, what that point would be when f is 7, when x is 7. Cool. All right, something like that. So this is what piecewise functions are. I mean, we've seen stuff like this before. We can draw that. We've done that topic before. We've done that before. But we are now just saying that certain different rules apply for different areas of the graph, which can happen. Right, moving on. Oh, one more thing regarding this picture here. If you look real carefully, this graph goes very close to 3. But at 3, remember, at 3, this 2x graph, this fx equals 2x graph, it doesn't actually have a value when it's actually 3. When x is exactly 3, so at this point being x equals 3, there's no value. We don't use this equation at all. We can't say, oh, the function goes up to 2 times x, 2 times 3, so 2 times 3 is 6. We can't say that that's the value, 6. We can't say that, because we know that starting from 3, this new equation starts to apply, right? So that's why we have, for this function, because on that actual point, once we reach 3, this function doesn't apply anymore, so we have this empty circle there. So it needs to have a blank in the middle. Now, this graph here, now let's look at that second graph, that x minus 1. This graph here, it does include the value for x equals 3. This point is included. If x is 3 exactly, we use this exact point, right? So what x minus 1 is the function. If x is 3, yep, that is indeed 2, or the function is 2. So that we do use. So we differentiate that. We show that difference by making that a open circle, like an empty circle, while this one here is a filled in circle. Because this one is included. And that's just how that's just notation. That's just how we draw this stuff. Cool. So moving on. Yeah, there's a lot of talking in the first parts of this, because a lot of this is relatively new, right? Notations and the way we write stuff. So cool. Now, drawing these functions. Now, the function is defined as follows, and we can see it here. Okay, let's do a evaluate. That's the thing. Now, what does that even mean? Now, again, we're heading back into notations again. Just the way we say things. You remember how that's the function? So if that's the function, if I say f with a 0 in the bracket, I mean, well, what's the value of the function when x is 0? That's what that means. That's what that means. So here we know the two equations. We can see the two equations on the left there. When x is 0, we don't use this one. This one does not apply. That's when x is greater than 1. So we use that first one. That first one being, 2x. This one applies. So let's check that in. So if I wanted to go f of the function when x is 0, this x here becomes a 0. times 0. Or you can just put it in a bracket, 0. Yep, so 2 times 0 becomes 0 plus 1, so it just becomes 1. There you go. That's A. Now let's move on to B. It should get easier and easier. Now again, we have to decide which equation are we using. And if you look carefully, when x is exactly 1, we again use the first one. So 2, and the x becomes a 1. So 2 times 1 plus 1, that's a 3. Boom. C, f equals 10. Not f equals 10, sorry. There you go. X equals 10. When x is now greater than 1 at this point, so now we're using the second equation. So this is pretty much it for piecewise functions. It's knowing which equation you're working with, because, well, they change. So if we are saying x is 10, it's the second equation that applies now. So it's going to be 10. I mean, I don't need to put the brackets in here if this is the equation, but, you know, just to be clear, it's 12. So that's C. So we're using the second equation, x plus 2, and then we're putting 10 into there, into that place of x. Okay, let's draw the graph. Oh, cool, I just copied and pasted it here, just a little screenshot so I can draw on it. Right, cool. Now draw the graph of this function. Now, remember, this is the point where x equals 1. So this is where two different equations will meet up. Cool. Now we work with that first one. Let's work with the first equation. When x is equal to 1 or less than 1. So all of this area here, all this way to the left, should be 2x plus 1. Right? As you can see on the left there. So 2x plus 1. Oops. 2x plus 1. So how does it go? We graph it. We graph it, but we just stop at x equals 1. We graph it as we know. So I know it's going to be at x equals 1, at x equals 0, I know that function is going to be right there. Yep. At negative 1, I know it's going to be there. I know it's going to be there and there. And I know it's going to be here, but I won't put an X there because I know I need a circle, some kind of circle. It's either filled in or empty, depending on where it's included. So I'll draw that line. I'll draw that line. Okay, yeah, I understand that's a very bad line. Let me try that again. No, that's actually wrong. Oh my goodness. Actually, it's not even there. Sorry, it should be there. There we go. Now that's the graph there. Now I know it's a filled in circle because as you can see, when x is 1, this graph, it says this is the equation that works. This is the equation we'll use when x is equal to or less than 1. So we have this equal sign in there as well. So when x is 1 indeed, yep, we know it follows that line. We know it follows that equation. Now starting from here onwards, we're working with x plus 2. So I don't need to work out when x is 0 or x is negative 1. I just need to work out this area. From here on, rightwards from here. Cool. X plus 2. So if I say 1, let's start at 1. 1 plus 2, it should be 3. Cool. It actually touches the same point. So I don't need to actually do anything with this dot because both equations go to that same point. So I can leave that point filled in. 2 plus 2 is 4. 3 plus 2 is 5. And then so on and so forth. Here's the new graph. And we draw it. We know it's a straight line graph because it's a linear graph. We just know that the gradients change. So there's a bit of like an elbow there. And that's it. That's drawing the graph. And now we have two separate graphs stitched on together. Like so. Right. Moving on. Now practice. Now I know you should try this, and you should, but I'll also Actually, no, this was your work as well, to be honest. Yeah, I'll still do it, but you should definitely try all of these again, yourself with a pen in hand. Cool. Now let's draw the graph again. I'm just gonna copy and paste. Cool. Now look at all these equations. We have 3 equations. Now, I know some of them don't look like equations. That second one looks very, very simple, but nevertheless, now between x being 0, including 0, that's an important point, including 0, x up to 1 is 2x. So I know it hits this point, because when x is 0, 2 times x is 2 times 0, that's 0. And then we know it goes up to 1, but it doesn't actually include the 1. So I'm going to leave that as an empty circle there. Okay. Now starting from that second equation, 1 greater than 1, less than 3, but also including 1 and 3. So if x is 1 or greater than 1, but also smaller than 3 or equal to 3, we know the function is simply 2. So it's a straight flat line. Now, because it includes both these points, I can fill them in now. If these two graphs link like this, sometimes you don't even need this circle at all. I can just draw this, and we understand. But since we've started doing this, let's just keep at it. Okay, from greater than 3 up to 4, but not exactly 4, not including 4, is 4 minus x. So cool. 4 minus x, if it's 3, it's 4 minus 3. That's here, but it doesn't include it, so that's an empty circle there. And I know that if it's 4, it should go here. Now again, that's an empty circle. That's an open empty circle, because if you look at the question here, we know it doesn't actually include the x equals 4. It gets up to it, so less than 4, but doesn't actually include when x is equal to 4. So I have to leave it like that. And that's the graph. So it's 3 graphs stitched together with allocated regions. Now, nonlinear piecewise functions, cool. Any function, including quadratics, parabolas, cubics, and others, can make up a part of a piecewise function. So it doesn't have to be linear. We could use mix and match all sorts of equations here, but it all follows the same kind of rule, right? The same kind of method. We do it the same way. There you have it, right? And as you can see here, like I said before, you don't see the circle there. You don't see the circle because the 2 lines, the 2 graphs, they do link up. So if they do link up, you don't really necessarily need to do those closed circles, dots here. So on these elbows. So like I said, I can ignore that dot there. But I really should do this one though, because that's where it ends. But I don't know if it includes the 0 or not until I put that dot in. This one I do need. And this one I do need. Because I don't know because these 2 graphs, they don't link up. So I need to know which one's the one I use when it's exactly 3. Anyway, there we have it. Moving on. Let's try some try nows, some more try nows. Here we go, try now, practice. The function is defined as follows, and we have that question there. Let's do it. A. F equals, not F equals, I keep saying that. So cool. X equals -3. Now, again, first thing we do, which equation are we going to use? We know it's the top one. So it's a -3 plus 5. So in the place of the x, I've put a -3 in, because that's what that means. When the x is -3, when the variable is -3. So if I put -3 into the function, which is the whole equation, if I put -3 into the function, what do I get? Which is what this notation means. Which leads us to 2. That's all good. Next one. That one. When it's exactly 1, we know we use the second one because that's when x is greater than -1. 1's greater than -1. So there we go. Let's try it. We know it should be 1 squared. which is just 1. There you go. C. Evaluate f0. Now f0, which equation do we use? That is greater than -1. So again, that's greater than -1. So there it is. We use the second equation. If x is 0, it's just 0 squared, which is 0. Boom. That's 3 marks done. Now, next one. Again, okay, let me just quickly... Let me just copy and paste it here. Now draw the graph of this function. Now going back to this function here, we know the cut line is going to be right there at -1. You can see that on the equation. Now cool. Now when it's equal to -1 or smaller, it's x minus 5. Cool. Sorry, x plus 5. So at -1, x plus 5 is, where is it? -1 plus 4. And if you do the rest, so at -2, if x is -2, -2 plus 5, so on and so forth, we know that's the line we get. Cool. Now, when x is greater than -1, we have x squared. So there we go. That x squared actually goes like that, like that, like that, and so on. And it curves upwards. Cool. Now let's draw these two. There you go. And then we have the quadratic that goes, oh, that's not good. True. Okay, cool. Something like that. Right. Now, we know that the first equation, the top equation, x plus 5, that's the one that includes the -1. So that's the one with the full filled in circle. And this one will have an empty one there. And there it is. There it is. Cool. So we've just drawn a part of a quadratic, and then we've also drawn a part of a linear graph. And that's pretty much it. Find the two values of x for which fx equals 4. Cool, we're saying fx equals 4. Now we can use the equation, but if we've drawn the graph right, it's quite easy. We can see on the graph already. Here's fx equals 4. Remember, fx is the same as y in our graph, so it's the result we get when we put the number into our x. So if we look at this line here, yep, there are 2 times when x is 4. Now I've drawn this wrong actually. This one actually passes right there. So it should go that because 2 squared should be 4. So yep, so what are the two values of x? It's when x is -1 and also when x is 2. You can use the graph to say that, but you can double check with the function, right? You can double check because at fx equals -1 for that first graph. Oops, nope. This is -1 plus 5 gives you 4. Yep, boom. And that second graph, it's 2 squared gives you 4. Boom. So we have these two graphs at 2 separate points. Yep, we're sure that -1 falls under that first graph. We know that 2 falls into that second graph. And yeah, there you have it. But you could also see from the graph. Okay. Oh, do you want me to keep going? You know what? Might as well. There's only one more, or 2, 3, 3 more. You know what? Let's do it. It's going to make this a little longer, but you know, you can skip it. You can decide to not watch this. So, applications of linear piecewise functions. A tourist operator hires out jet skis as follows. It costs $150 to hire a jet ski. This allows the customer to use a jet ski for 3 hours. The cost for the cost for use for longer than 3 hours is $40 per hour. So up to 3 hours, so this is just me now, up to 3 hours, there's a fixed cost and you can hire the jet ski for 3 hours. But then from there on out, it becomes a per hour function. All right, let's keep reading. This is calculated exactly. So that 15 minutes, for example, would cost exactly $10. Cool. Cool. So it's not chunked up into hours. It's down to the minute. The costs are given by the following piecewise function. There it is. Cool. The D's on there and A's here. So let's do A first. There we go. Okay, let's draw the graph. Okay, so up to x, not x, when t, up to t equals 3, we know it's 150. So we have this straight line here, it's just straight up 150. Now from here on out, it's 40t plus 30. So I wonder what it is at 3. Let's chuck 3 into t. So 40 times 3 plus 30, which is 120 plus 30, which is 150. Okay, cool. So we know it links up. So from here on out, we know it links up from that point, and then I guess it goes upwards. It's a linear graph. It's 40 times t, so it's every t, it's going to go up by 40. So let's try a few. I could just try any other point at this in this stage. So I don't know. Let's pick 8 because I feel like it might be easier to do that multiplication. Remember, for a linear graph, I don't need too many points. I just need like 2, because I know it's a straight line. So if t is 8, what do I get? That's 320 plus 30. That should give me 350. Cool. Or dollars. That's to be precise. So 8 equals all the way up here. When t is 8, we know the graph crosses right here. So I know this graph goes oh, that's not very good. Now I know that's not a perfect straight line, but we get the point. That's the graph. All right, awesome. B, what does a customer pay if they hire a jet ski for 10.5 hours? Now, this goes beyond the graph. The graph ends at 9, so we don't know from the graph what 10.5 hours looks like. But we got the equation, we got the function here, so we're good. So if t equals 10.5 or 10.5, is that equal to or less than 3, or is that greater than 3? Of course, it's greater than 3. So we ignore that first line, 150. We just work with that second equation, because that's just the one that matters to us. So at 10.5, it is, bracket, let's just say 10.5, just to avoid fractions at the moment. 3, here we go, and we chuck that in. That becomes 420 plus 30. That's $450. Cool. It costs $450 to hire a jet ski here for 10.5 hours. Cool. Next one. That's B, by the way. C. A customer pays $220 to hire a jet ski. How long did they hire it for? Okay, cool. First, to figure out which function we're using, or which equation out of the two, we look at the graph and and to see that at $220, which is somewhere in here, we know it's more than 3. We know it's not this area here. We've gone past that. So we know it's going to hit somewhere around here. Now, I know the graph isn't exact, so we can't work with it, but at least we know we're going to use that second equation again. We're not going to use the first. So we're going to say it's $220. That was 40 times t. Oh, I don't need the bracket anymore, sorry. 40t plus 30. So whatever t was, we ended up paying $220. So we're putting that over there in the place of the f or the y, depending on how you're writing this equation. So let's minus the 30 both sides, which I get 190 40t. Yep. And then I divide by 40, which is something or other, which is 9 over 40, which is, oh my. What is that anyway? Let's do it on the side here. 40 divided by 190. Cool. Is it 4, 5? And so that's a 3, 0. It's a none. Not. It's a not. 300. Oops. Which is, well, ignoring the decimal point, I know it's going to be a 30 over 40, which is just 3 over 4. So I know it's going to be 4 point, so I know t is 4.75. T. Oh wait, I should really say hours. Yep. Cool. Yep. So it's 4.75 hours. I mean, you could be more precise about that. That would be what 3/4 of an hour is. It's 4 hours and 45 minutes. Oh, that's not how you spell minutes. But minutes. What am I saying? Yeah. Equals t. Or better yet, t equals that. Yeah. There we go. All right, there you go. That's C. The tourist operator also hires out kayaks. The rate includes 2 hours use for $40, and each additional minute costs 30 cents. Cool. Write a piecewise function for the kayak rate. Okay, so if t, let's say we're still using t equals hours, like t is hours. I mean, we could change it to minutes, but let's say we keep it the same t and the same function. Cool. So we write something similar, right? We know something like this, and we just copy it out. We do something like that. The rate includes 2 hours used for 40, and then each additional. So we know it's the same kind of format, just different numbers. So it's $40 for up to 2 hours, right? So this includes 2 hours. If they used it for exactly 2 hours, they would also pay $40. They would not pay more. So including 2, it costs $40. Anything under 2 hours, $40. Now, we have to think about something different now. Now we have to think of a linear equation that goes from that point, goes from the 40 point onwards. Okay, now to make that, of course, we know how to make our linear equations. It's something like that. And we're just checking in the right numbers. I know x should be t at this point, but because we learned it as this, I just want to bring out that format just so we see it. What is the gradient? How much are we paying per time, right? It's 30 cents per minute. So remember, our t is not in minutes; it's in hours. So in an hour, how much extra are we paying per hour? That would be what, 30 times 60, right? 180. No. Yeah. 1,800, not cents, not dollars, cents. So yeah, don't forget that. So that means $18, right? Because this is cents. So we're talking $18. Whoop, that's so bad. Let's try that again. It's $18 per hour. Cool. So we know that M should be 18. Yeah, let's change that to T now. Now, I don't know what C is yet, but I just know that I want it to match exactly that. So when T equals 2, I want it to match that. Oh, let's draw it down here. If there's a graph and it's 40 here, I want this linear graph to match here and then carry on upwards. We know what the gradient, we know what the curve, the slope we want, which is 18, but I gotta make it so that it does this. It does actually meet up at that point. So let's substitute in. Actually, I shouldn't have erased that. I'll just leave that there. Let's substitute the value we want. So when t equals 2, I want y to equal exactly $40. Yep, it was 40. Yep, right, because that's 40 there. So when t equals 2, I want it to exactly match up to 40. I chuck that into that linear equation that we are making for the second portion of that graph. It's 18 times 2 plus c. Yeah, because we need to find out c. That's the point of this. So 40 equals 32 plus and equals minus 32 from it. So we know 8 equals c, or better yet, c equals 8. I mean, at this point, I'd flip it. So the whole equation should be, we found m because that's how much we're paying per minute or per hour. C equals 8. So here it is. We know it should be 18t plus 8, right? Yep. When t is greater than 2. And boom, and that's how you write it, right? So this is just pretty much finding a linear equation is only the chunkiest bit of this. But then we're just piecing it together like in this format, like this, as a piecewise. So we just have to make sure we know what these mean and how to write it as such. Cool. Next question, the second one. Cool. A mobile phone operator offers customers a choice of 2 monthly rate plans. Name of plan, buffet, cool. Description, pay as you go. Yep, each text, Yep, so there's some details. The equation for the buffet plan, there it is. All of that, you can read it, where C is the monthly cost for the user and X is the number of texts. So it depends on the number of texts that they send. Cool. Right? So a la carte is actually, if you think about it, is just a linear graph because it's just easy. Each text costs 10 cents and there's no other complication there. So just 10 cents per cost, and that's it. So we can imagine that being quite simple. Oh, they're using C, so I'll use C, right? Oh wait, no, you know what? That's the first question. So let's do the first question. Write the equation for the a la carte plan. Now, so the graph is already drawn for us. Cool. If it's simply 10 cents per text, that's a linear graph. That is 10 cents. Oh, the cost is in dollars, so we can't say 10. We want to say 0.1 times X. Oh, let's C equals. Cost equals 0.1 times X. You can also say C equals, I don't know, like that's the same thing, right? Oops, sorry. This is the same thing. It's really all the same thing, but we get it, right? Every time X goes up by X goes up by 0.1. Oop, losing my words. Okay, B. Cool, now we're recommending plans. Cool, not only do we have to say which one's better, we also have to say how much they would save. Now, Gary is going to have 200 texts per month. Cool. Okay, if we look at the buffet plan equation, that's the first equation. We know Gary's going to pay 30. So it's going to be 30 versus, so the buffet plan is 30. A la carte would be times 200 texts, so that's $20. So this is buffet, this is a la carte. A la carte. Okay, cool. So we know should go with Go with a la carte, saves $10. Right, saves $10. If you went to buffet, Gary would be paying $30. Cool. Next one, Hidemore, $4.50. Okay, cool. Let's go. Let's figure out the buffet one first. At $4.50, still we're working with the same the first one, the first equation. So cost is just that. As opposed to, let's have a look. C equals 0.1 times $4.50, which is $45. So go with the buffet. That's a tick for the buffet. That saves $15. And we carry on. Chinois, $5.80. Now, on the buffet plan, now we're actually greater than 500 texts. We are in a different equation now. We're using that the second part of that equation, that bottom line. Cool. So let's go 0.2. Oh, cost equals 0.2 times 580 minus 70. And cool, we have to do a bit of math here, bit of calculations. It's all math, but it's a bit of what you call it, calculating. What is it? Da. Da. There we go. Oh my goodness, that took me much longer than it should have. Oh, yep, this is buffet. I forgot to label it. Wait, what have I done? Oh, wait. That's 580. So sorry, there it is. That makes better sense. Yep. So that comes to $46, right? And for a la carte, it is simply, which is $58. Yeah. So go with buffet. Saves how much dollars? $12. And we carry on. So now we know what's happening, right? But again, practice, do it yourself as well, so we get the hang of it. Let's work out the buffet plan, and then we'll work out the a la carte plan. Buffet plan, it is 800 texts, so we know we're working with the second line. Its cost equals 0.2 times 800 minus 70, which is $160 minus 70 equal because it would have been that. Yep. $90. Cool. That's a lot of texts. Yeah. A la carte, there it is. C equals 0.1 times 800, which is $80. So buffet is the way to go. No, sorry. A la carte's the way to go. It saves $10. Okay, cool. There you have it. And that's how you do it. C. For what value of the X is the a la carte plan a better deal than the buffet plan? Include an explanation of how you worked it out. Okay, now if you can look on the graph, right? We know it's better from some point, I don't know, so some point a little higher than 300-ish texts and up to like 700 something texts, it seems. Buffet is cheaper. But for less than that and more than that, so we want to know those intersection points. So if we see the graph, what I mean is that's a la carte. We have this happening. So if we can find these points, then we can say which areas we're looking for. So the points where a la carte is the better plan, it's this area, and it's anything larger than this. Yep. And of course, not that middle area. Not this middle area. In the middle area, you can see that buffet is cheaper. It's a cheaper plan. Cool. Now, to find it, we are now looking for points where the graphs intersect. So that first dot there, c equals 30 is the buffet plan. C equals what are we doing? Where's the thing? Oh no, of course. Sorry. Is the a la carte plan. So we want to put these two together. We just substitute this in. So I'm just gonna join them up. So I get 30 equals 0.1 t, right? Because if this c equals this c, then 30 surely is equal to that. That c I can say is 30. Because we're looking for the point where, oops, I probably erased more than I wanted to. Because this point here, we know that the sloped line, the a la carte line, should reach exactly 30. That's when it would cross. Because the buffet line at that point is just a flat line. Cool. Anyway, let's work it out. T equals, it should be 30 divided by 0.1, which is the same as timesing by 10. So at 300 texts, not tests, texts. Cool, we worked that out. Let's just mark it at 300. Now we want to know this point here. Let's work out that one as well. Now we know buffet has moved on to its second equation. So we still got this for our a la carte equation, but our buffet equation is now, oops, sorry. Oh, right, no, sorry. I don't know why I put x there. I know we've been using t. Have I done that for everything else? Hope not. Oh my goodness. Just realized. Yeah, just from the last equation, I think I just it eluded me. Anyway, that's the equation we want, and we want the two to meet. So we know that this should be equal to that, right? Because they should both be the same c at a certain point of x. At a certain number of x, those two c values should be the same. So we have something like this. Right? Let's move it around. I'm going to add 70 to both sides. I'm going to minus 0.1x from both sides. I'm going to minus it. So that's 70 equals, right? If it's 0.2x minus 0.1x, I get 0.1x, right? Which is what I'm just doing. There we go. So x is 70 over, right? I want to divide by 0.1, which is 700 texts. Cool. So we have the 2 points. Now going back, that's 700. So a la carte is a la carte has a better deal. Better when x is less than 300. When it is exactly 300, remember they are the same deal. It's not necessarily better. So I'm going to say it's less than 300, or x is greater than 700. Boom. There you have it. Now, D, a competing mobile phone operator decides to undercut these rates. They will offer a pay-as-you-go rate. So that's the same as the a la carte rate. If you look at it here, pay-as-you-go, that's the same as the a la carte. They want to make as much money as they can per call, but their rate has to be no more expensive than the rates shown in the graph. Add a line to the graph that meets those requirements. What's the equation? So they want to make it a pay-as-you-go, so it's going to be a straight line that goes from the 0. Cool. We know that the current graph looks like this, but they want their straight line that starts from here to be no more expensive than any of these plans at any point, but also the highest it can possibly be. So of course, if you think about it, it's going to be right there. It's going to touch that line. It's going to touch that point right there and move along. Wait, I'll change the color. Wouldn't that be smarter? It should be like that. That's the new graph we want to make. All right? Cool. So we think about it. We know it's just going to be a linear equation. We know C is already 0 because we know it's going to start from the origin, from 0, because it's a pay-as-you-go plan. So we know that's gone. Now we know the gradient needs to be something, but we want it to hit that corner. We want to hit that corner right there. Now, if we look at the equation for the buffet plan, that occurs, that elbow, that curve, that turn occurs right at 500. And it happens at 30. Right? So we want our y to be 30. We want our y to be 30 when our x is 500 for our new graph. This is the new graph that we're trying to make. All right? We want this to happen. So let's chuck that in. Let's see what gradient we need for that to happen. Cool. It's 30 equals m, the gradient, times 500. Cool. So m equals 30, not 330, divided by 500, which is something. I mean, it's 3/50. Do I want to work with this? I don't think I need to. I mean, I wouldn't mind sticking with this. So I would just say the equation is 3/50 times x. This is the new pricing plan that they need. It should be $3/50 $3/50 per text. Or they can say, so because they just asked for the equation, I can say this, but I mean, or you can say it's 6 cents per text, right? Because 3/50, if you make that, that's the same as if you make it over 100, that's 6/100. So that's 6 cents per text. But anyway, there you have it. Back to blue. E. The competing operator also offers a text 200 plan. The first 200 texts cost $10, and additional texts cost 25 cents each. Write the piecewise equations for this plan. Cool. Function. Oh no, actually no. We've been using C for cost, so let's do that. So this is what we're going to get used to writing, and of course that needs practice. Do more of this and more of this as we go. We know for up to 200, it's just $10. So C equals 10. C simply equals 10 when x is less than or equal to 200. Now, when x is greater than 200, it costs 25 cents each. So again, we have an equation to make here. We have an equation to make here that is C equals mx plus, oh, let's not use C. Let's not use C here, actually. Let's write that. Cool. We want an equation here that when y, that the gradient is, we know it's 25 cents each text. So we know that is 0.25. We know m equals 0.25. Also, Also, we want y to equal exactly 10 when x is 200. Because we want to know, we know that we want to link these two graphs and they should meet there. So this is, if that was a graph, that would be at the point 200. And that's 10. So, and we want this equation to line up there and then move on upwards. Cool. So, chucking all of that into this equation, y is 10, m is 0.25, x is 200, plus c. Yeah, I reckon we can find c from that. So 10 equals 50 plus c. So c equals, well, negative 40. Awesome. There you have it. So we're back up here now. We're back up here. So we got our m, we got our c. So we know what our equation needs to be. It needs to be 0.25, that's our m, x minus 40. When do we use that, do you ask? When x is greater than 200. And then boom. So right, so again, just recap. When we use this graph, if it's less than or equal to 200, we just read it like that as a straight line. If it's more than 200, we read it like this as a straight line. Right, and we forget about the other one. But there you go. That is it. Boom. And that's all the questions. I hope I got them all right. Would it be weird if I got them wrong? No, it looks right. Anyway, I hope that helped. If some of it still doesn't make sense, or there's something you want me to just spend a little more time on, let me know. But otherwise, there you go.